So let's continue with the tree iterator. So we're going to create a private class tree iterator implements iterator of type T. Just going to be an inner class, so just do it before the last bracket, I think. So here we'll have some fields, some private fields here. So we'll say private int expected mod count and private iterator of type T iter. So for the constructor, we'll say set up this in iterator using the specified iterator at param iter, the list iterator created by a tree traversal. So here we'll do the constructor. So we'll say public tree iterator we'll pass in iterator of type T iter, so it's going to take an iterator named iterator of type T. So that's going to be we imported the java.util class, I believe, so we can access the iterator class now. So that's a built-in method and built-in object. So we're going to use. So we're going to say this dot iter. Excuse me. So this dot iter points to iter, and expected mod count points to mod count. And we'll override the methods that we're supposed to implement when we implement iterator here. And we've also implemented iterable, which allows us to implement an iterator. So it's going to be awesome. We're going to implement these iterators and we'll be almost done. So we'll put the next method here. So we'll put returns true if this iterator has at least one more element to deliver in the iteration. At return, actually whoops, forgot, put that up there. So we'll say at return true, so it's a boolean. Boolean has next. You've used it before, maybe with scanners, or you've used it with iterators itself. Scanners are maybe they're iterable, they probably are, and they've implemented that in the scanner class, so you can use has next and next. Probably remove too, so you can type here. So if this iterator, return true if this iterator has at least one more element to deliver in the iteration, and we'll say at throws concurrent modification exception. That's a built-in exception. Modification exception. If you're following the series, we've talked about that before. I'll try to make this into a playlist. I've actually never made a playlist before for videos I've made, so I'll try to do that. If not, just go back, start with the link stack, or the because we did array stack before. We've already did one data structure, but it wasn't in the series because arrays itself, they are a data structure. But then we talk about concurrent modification, maybe in the linked list or array list. Both of those, I think we talk about it. So what happens is if the collection has changed while the iterator is in use. So if the mod counts, I think, are unsynced, so if they're not the same, or if the iterator is used while the, so if you're saying while has next system.out.print next, or save it to like temp and return temp as a string or something, then if you, while that loop's happening and you modify it or something, it can throw an exception, so just be careful. So here we'll say public boolean has next. I think this is an override, and it throws concurrent modification exception. Did I spell that wrong? Concurrent modification modification. Yeah, I did. Modification exception. So it's just remember concurrent modification goes with iterators and iterable. Anything iterators, it will throw the exception. So for extra credit or points, just throw this in every method, and you should be good. So here we'll say if not mod count, if not. So we'll just say first, if not mod count is equal to expected count. So what are we saying? Expected mod count. Expecto Patronum. No, I'm just joking. So if mod count is equal, or if mod count is equal to expected mod count, so what is happening there? So we just have, I think we might have changed the name for it before. So we just have the mod count. It's technically a global variable for this private inner class. It's a field. So we could have named them the same thing and used this, but they do it differently. So we're just saying if mod count does, so if mod count does not equal to expected mod count. So all this unary not operator does, unary, whatever, it says if mod count. So if it says it's the opposite, so it takes the opposite of what is currently happening. So if it says if mod count is equal to expected mod count, then the not means if mod count is not equal to the expected mod count, right? So if these values, this mod count and the mod count global, I think that's from up here. Yeah, it's up here. So we're accessing variables within two classes within the same class. So it's a little tricky because we don't use inner classes that often. But I think really we could have said if this dot mod count, maybe. If this dot mod count equals to this dot expected mod count. So it doesn't like the this, but if just mod count is, just remember that it's referring to the mod count up there. But yeah, so just remember the mod count is referring to the global mod count for this data structure, which is a linked binary tree. That's all you have to remember. This doesn't work, I'm not sure why, but that's okay. You can test, you can trial and error a lot of stuff as you go. That's gonna happen. Especially if you're switching through languages a lot. So here if you say, you could say this, but you don't need to, because we already know it's this one, because we only have one. And it's the global variable for this private inner class. So if mod count is not equal to expected mod count, which means if the values are different, in which they should be the same, because we're going to increment, mostly increment them. I don't think we're supposed to decrement them. According to my professor, because the book was wrong. So we're just going to be incrementing them all the time, and if one's like 2 and if mod counts 2 and expected mod counts like 3, then it's going to throw the exception. Pretty sure that's what happens. And then also if you use it while the iterator is being used. So here we'll throw concurrent modification exception. So if mod count is not equal to expected mod count, what's up with this? 2 brackets maybe, parentheses. So if that happens, throw that, and if they are the same, which they should be, then return iter dot has next returns true. So this is a boolean again. So this method returns true or false. So we're saying return true if returns true if iter has next, or has or let's say if iter is holding a token. I think that's what they say, tokens. Or we could just say if it has an object. So this method has next returns true if iter, which is the iterator up here. We have a private iterator of type T named iter. So just remember we're accessing a class object within the Java API. It's already built in. That's why sometimes working with stuff you don't create is a little confusing. So it's just built in. You can look it up on the Java Oracle docs. Do they tell us anything here? So an iterator is an iterator over a collection. Iterator takes the place of enumeration. In the Java collections framework, iterators differ from enumerations in 2 ways. Iterators allow the caller to remove elements from the underlying collection during the iteration with well-defined semantics. Method names have been improved. The interface is a member of the Java collections framework, and enumeration can be converted into an iterator by using the enumeration. Okay, some random stuff that we don't really need to know. An iterator just iterates over the elements of a collection or the objects of a collection. That's all it does. It's built in, right? Can I pull up something? Actually, I don't even have my browser open. So just remember it iterates over the elements of a collection. I think that's the exact definition. That's what an iterator does. And to implement an iterator, you need the class to be iterable, which means you need to implement the iterable interface. And then implement java.util.iterable first. Actually, maybe both, just iterator and iterable. So just import the whole java.util.star class. Then once you do that, take your private inner class, which what we did, implement iterator, create your object reference variable iter of type iterator, of type T, or whatever of type you want. Then the next step is to override the has next. So you just need a mod count to keep track of it in your methods, which we will be doing in our linked binary search tree. Right now we don't have any mod count. Any increments, I don't know if that's a word, incrementations of the mod count variable. So we haven't been adding any elements or removing anything yet. This is just the basic operations of the tree, which we're going to extend. So if you understand that. So after all that, all has next does, it just keeps track. All the iterator does is, if I've explained how to set it up, it's going to iterate over the objects of a collection, or the elements of a collection. We're going to create a private inner class. You can call it whatever you want. We call it tree iterator. You have to implement iterator. Then once you do that, you have to override these classes. And we've discussed has next. So iterator has its own has next. So we're just going to say, we're going to override that. So we're just going to say return our iterator. Returns true if the iterator has next. So java.util.iterator returns true if the iteration has more elements. In other words, returns true if the next would return an element rather than throwing an exception. So I believe that's a built-in method, not the one we have here. It's actually built in internally. So it's a built-in method. It's a little confusing, but that's how you set it up. So we're going to be using it. It's just an internal method you're going to use. This is how we set it up to work with the collection we're creating, or a data structure we're creating. So hope that helps. We're going to be using it. I should have some other examples. I might just do its own video. We still have to. I might still do the link stack and the link list, the singly linked list with head and tail. No previous reference. I'll do the iterator, maybe a few examples before I upload that, and I will try to do some for the array list as well. Otherwise, there's just a few ways to use it, like in the toString, you can use it and stuff like that. So hopefully we'll find an example of that pretty soon. Here we're going to use it to traverse. We're going to do some traversals with it. We may not do it at this exact time, but we're going to set them up. So here we're going to say returns true for the next method. Actually, sorry. We're going to say returns the next element in the iteration. If there are no more elements, returns the next element in the iteration. If there are no more elements in this iteration, no such element exception is thrown. Return the next element in the iteration at throws no such element exception if the iterator is empty. So public T next throws no such element exception. So if has next, so if it has an element if our iterator is holding an element or a token, an object, then return. I think this is a built-in method here. Return iter.next. It should say iterator. Java.util.iterator. I believe, yep. Java.util.iterator. So that's in the built-in class. That's in the built-in class. Sorry, there's someone, my nieces just came over. Doorbell was ringing. So if has next, return iter.next. Then we'll say else. Throw new no such element exception. So this iter.next, it just returns the internal the internal method from .util.iterator of type T. So it just returns the next element in the iteration. So all we're doing is we're just setting up the internal methods to work with our data structure itself. So it's nothing too hard, hope you understand. So now we'll just, we're basically overriding, but I'm not sure if it caught that in the, okay, so technically we're overriding, but what we're really doing is implementing. So that's what it's saying, but these methods are already created. We're just setting them to work with the way we want to use them. So here we'll say the remove operation is not supported, so we're not going to use the remove operation in this structure. We're just going to throw an exception for it. So we'll say at throws unsupported operation exception. Unsupported, sorry, just turn the light on here. Unsupported operation exception if the remove operation is called. So throws unsupported operation exception if the remove method is called. So that's it, we're not going to be using it in this implementation of our tree. So we're just going to say public void remove, and here we'll throw new unsupported. Oh, so I do have the iterator 2 string. Sorry, let me just turn the light on. The time changed and the it's getting dark here faster. Okay, so here we'll throw new unsupported operation exception. Unsupported operation exception. So public void remove, throw new unsupported operation exception. That's it, that's all we need to do. You can system.out something, a string if you want. And here we'll just say public string to string. We'll just override this method as well. So this, we can do some doc for this. So it just says returns a string representation of this linked binary tree. At return str, that's all we need. We can do an at override. At override. I don't do that to all of them, since it's just practice. But if you're doing this for something professional, you can override them for the doc. So public string to string. Then here we'll say string str points to empty quotes. Then we'll say while iter. We'll call our iterator. So while iter.has next, so we'll call the method. Then we'll say str points to str plus iter.next. We should have done this before, maybe not recently. Plus a space. Then we'll return str. So it's just going to print out when the iterator prints, when we want to print using the iterator, it's just going to iterate over the element, so it's going to check while our iterator has a token or has an object. Then if it does, then str, our variable that we created, which is a string, saves the data and prints it with the next element in the iteration, plus a empty space, and returns the string. That's it. So that should be everything in this linked binary tree. So we need to iterator, or sorry, we forgot a few of the tree iterators, so we'll just do those. So we're at toString. Let me just go up in my notes. So we have find node here. Private binary tree node find node. Public string toString. Then under that we have our iterator. Then under that we should have, now we're back here at our public iterator of type T, generic type T iterator in order. So we instantiate it an array list here. Call a temp list, so of type T. Call a temp list pointed to a new array list. We instantiate an array list. We call in order. Root, passing in root as a parameter and temp list. And here we'll return new tree iterator, temp list.iterator. And it's asking for in order. We'll do that right now. So we'll do some doc here. It says performs a recursive in order traversal. So takes node as a parameter, the node to be used as the root for this traversal. Whoops. That's what happens when you type multiple sentences without looking at your screen. Or yeah, I'm always looking at the notes most of the time. So at param temp list, excuse me. So temp list, a temporary list for use in this traversal. So it's a protected method, so we'll say protected void in order. Takes parameter binary tree node of type generic type T node, and we'll pass in an array unordered list. It takes an array unordered list of type T, named temp list. We can name whatever you want. So we'll say if node does not equal to null, then call in order. So it's going to call itself recursively node.getLeft and pass in temp list. Then we'll call in temp list add to rear. So temp list has an add to rear method in our array list that we created before. So node.getElement. And here we'll say in order. Again, node.getRight. So it's first it's going to traverse the left edge, and then after it's going to add it to the list, and then it's going to traverse, do a traverse roll of the right edge or the right branch. So we'll say node.getRight, pass in temp list, the list, and you can just use any list, it doesn't really matter. That's it. So we'll do the next one. There's 4 of them, so that's one of them. So it comes with an iterator, comes with a method that returns an iterator, and a method that actually performs the actual traversal. And what it does, it just returns the temp list.iterator. So they're just methods being passed around. That's it. So what's really happening is a traversal is happening here, and this is just returning all that data as an iterator. And putting it into a list. So now we'll do a pre-order traversal. So it performs a pre-order. Traversal on this binary tree by calling an overloaded recursive method. That starts with the root. So at return, a pre-order iterator over this tree. So create a public method of type iterator of type t. Call it iterator pre-order. We'll instantiate another array list here. Array unordered list of type t temp list points to new array unordered list of type t. And we'll call pre-order, pass in root and temp list as parameters. It's asking what pre-order is. We're going to do it right after we finish this line. So it's the same thing. We're going to create its own method to do the traversal. And here we'll just return new tree iterator and pass in temp list dot iterator. So here we'll say return or performs a recursive pre-order traversal. At param node, the node to be used as the root for this traversal. At param temp list, the temporary list for use in this traversal. So here it's another protected method, so protected void pre-order takes binary tree node of type t node, so it takes a node of type binary tree node of type t, and an array unordered list, so it takes an array list. We'll call it temp list again. We'll say if node does not equal to null. So if our node is holding an object, or if it is a node, if it is part of the either the root or the left or right child, one of the branches somewhere, then we'll say temp list dot add to rear node dot get element, so it's going to return the element that it's holding at its memory location. Then we'll say pre-order node dot get left. We'll pass in temp list. So pre-order, we're going to call itself pre-order, pass in the left edge or the branch, and pass in the array list. And then we'll call pre-order again and pass in the right branch or the right edge and pass in temp list again. That's it. Next one we'll do post order. So we'll say performs at post order traversal on this binary tree by calling an overloaded recursive method. Post order method that starts with the root. Oops, forgot at return. So at return, a post order iterator over this tree. So public iterator of type T, iterator post order we'll call it. We'll pass in, we'll instantiate an array unordered list of generic type T named temp list, and we'll point it to new array unordered list of type T. And we'll call post order root. We'll pass in root as a parameter and temp list. So again, we'll do the traversal below, and we'll return new tree iterator of temp list.iterator. We just have some water real quick. So return new tree iterator, pass in temp list.iterator as a parameter. Then below we'll do the actual traversal. Okay, so we'll put here underneath. We'll put some doc again. We'll say performs a recursive. So we can walk through this in the debugger if you're confused. So performs a recursive post order traversal. At param node, so it takes node, a parameter node, the node to be used as the root for this traversal. And it takes a param temp list, the temporary list for use in this traversal. So protected void post order we'll call it. Well, it takes a binary tree node of type T, takes a node, a parameter, and an array unordered list, unordered list of type T named temp list. So if node does not equal to null, then call itself post order node.getLeft. So it's like a trick basically. So it's gonna if the node you passed in, if it's not null, then it's gonna call itself with the parameters. So if that node, let's say we're calling in the left branch or the left edge. So if we call in the left edge, then it's gonna start again, and it's gonna say if that node does not equal to null, then again call another post order .getLeft. So if that one is not null, and it's gonna keep going until it prints each element until it's null, and then it's gonna go back to print the next one. So we can walk through that. We can try to walk through that in the debugger. So we'll just say post order here. Again, node.getWrite. And we'll pass in temp list. Then here we'll say temp list dot add to rear, and then node.getElement. So we're going to add the element that the node's holding to the list. That's it. Done. And the last one, it's a little longer. I don't think it has two parts to it. So it's done in one method. It doesn't have like a two-part method with the support method. It's just done in one. So here we'll say performs a level order traversal on this binary tree using a temp list. At return, a level order iterator over this binary tree. At return, a level order iterator over this binary tree. So here we'll say public iterator. So returns an iterator object of type T. We'll call it iterator level order. Then here we'll instantiate another array list. So array unordered list. We created that before. But we're going to say of here, we're going to change it. We're going to say array unordered list of type binary tree node of type T. Nodes points to new array list or array unordered list of type binary tree nodes of type T. So what's happening here? It's a little confusing. It's advanced generics basically. So all it is, it'll come natural if you practice, but all it's saying is what we usually do here is we just say of type T. But we're saying we want the array unordered list to store objects of type T. But here we're saying we want the array unordered list to store objects of type binary tree nodes, which those binary tree nodes are storing objects of type T. So hope that makes sense. We'll go to the next part. So here we'll say array unordered list. Again, if you don't understand, the best thing to do is just set some breakpoints with the debugger and just step through each part, see how the memory locations are changing. Here we'll put array unordered list of type T temp list points to new array unordered list. So it looks like it's creating two lists. And here we'll create an object reference variable, binary tree node of type T. We'll call it current, and right now it's set to null. So here we'll call nodes. So what are nodes again? Nodes is our array list, the one with the double type, or the object within an object. So it's storing binary tree node objects which are storing objects of type T. Could be anything, string, int, double, floats, whatever. So here we'll call nodes.add to rear. We'll pass in root. And then we'll say while, we can put that above here. So we'll say while nodes is not empty. Current points to nodes.remove first. So remove first is our array unordered list method. Nodes has its own is empty in its array list class. So nodes is storing a binary tree node, right? So here we're going to store the whole root. So while nodes is not empty, current points to nodes.remove first. Here we'll say if current does not equal to null, temp list.add to rear. Add to rear current.get element. Current.get element. And we'll say if current.get left does not equal to null, nodes.add2rear, current.getLeft. So what it's doing is just saying current here. That's our object's reference variable, points to null. Then here it says, well, the array list is not empty. Current points to the nodes.removeFirst. Well, current is not equal to null. So it's just switching the elements from one array list to the other. So if current.getLeft is not equal to null, nodes.add2rear. So here the traversal is happening getLeft. That's of type binary tree node. So we're not using the one from the linked binary tree, the method from that class. We're just using this one to traverse from the root down to the left child. Then we're going to add it to the list. Then here we'll say if current.getRight is not equal to null. Then we'll do the same thing, nodes.add2rear, current.getRight. Then after all that we'll say else. So if current is null, then temp list.add2rear, and we're just going to add null. Then after all that we'll just return new tree iterator, temp list.iterator. So if you're having difficulty understanding what's happening, again, just walk through the debugger. Hopefully we'll have time to do that. We can pick maybe one. If we can do this one, we can pick one of these. That should be all. So now we're at almost an hour. Let's see what else. This one should be done. So it's a lot. So it's 400 lines in this one. So it is a longer class. The rest of them are just small ones. So let me just find it. Well, I think we're going to do linked binary search tree now. So here we are. So we've done array list, unordered list, binary tree ADT, binary search tree list. We haven't done search tree list, we will. That's an easy one, just a few lines. Binary tree ADT, binary tree node we've done. The exceptions we've done. Linked binary search tree haven't done. Linked binary tree we've just finished. Linked list ADT we've done. Main we haven't instantiated anything yet. Exceptions were done. Diagram. I haven't done a diagram, but we have everything else. I'll try to do a diagram as well. So we'll start by creating a new class called linked binary search tree. So this one is a little bit of a longer one. Actually, I have a special one that I made. I think it was yesterday. I called it best tree. One sec, sorry, it's just opening. Hopefully it isn't too long, because it's taken us a while just to do that one. It's not too bad, maybe a little long. So this will conclude our linked binary tree after this class we're gonna do. Then we'll do the heap later on, and I think we'll come back to this class. But the tree list thing, that's just an easy one. We're just calling methods we already. It's like an internal queue that we just use the java.util methods. So here we'll start by creating a new class. Linked binary search tree of generic type T. So you can right click your src folder if you're using IntelliJ. VS Code, it should be similar. So we'll just type in linked binary tree. Linked binary search tree. .java. Hit enter. Then you should get your class. So I'll just redo it. So here it says public class linked binary search tree of generic type T, and we're going to use the extends keyword to extend linked binary tree. So a linked binary search tree is a linked binary tree through inheritance. We'll say of type T, and we'll implement. I might have changed the names around, but we'll implement. We'll say implements binary search tree ADT of generic type T. So here we'll say creates an empty binary search tree per doc, creates an empty binary search tree. We're going to overload the constructors. But here we're just going to call the super reference, so we're just going to reference the class name for the constructor, so public linked binary search tree. Call super. Super is going to set up the superclasses, instance, fields, and data. Then here we'll create an overloaded constructor, so it creates a binary search tree with the specified element as its root. At param element, the element that will be at the root of the new binary search tree. So here we'll say public linked binary search tree. So it's an overloaded constructor. This one's going to take parameters T element. Whoops. So it takes a parameter so it takes a parameter element of type T or T element. We'll call super again. We'll pass an element because remember the linked binary tree also has overloaded constructors. So it's going to find the one that takes one parameter. Then here we'll say if not element is an instance of comparable. So it's saying if an element is an object of comparable, so instance of just means object of. So it's saying if element is not, so we have the not operator, so if element is not an object of comparable. So if it's not a comparable object, then throw new non-comparable element exception. Then pass in linked binary search tree as a string. That's it. We don't really need a brackets there since it's just one thing. So we just leave it like that. Should be fine, unless there's no red underline, so it should be fine. I've already tested this before, so here we'll just do the add element method. So there's two of them. One has a private support. One is a private support method. So here we'll just say adds the specified object to the binary search tree in the appropriate position. Forgot how to spell. Okay, it's fine. Appropriate position according to its natural order. Note that equal elements are added. At param element, the element to be added to the binary search tree. So element, or you can call it obj, object, whatever. Element, so we'll just call it element. So it takes a parameter element, the element to be added to the binary search tree. So if your app has a data structure to store data, then you can add whatever here. Strings, numbers, whatever. Objects. So here we'll say public void add element t element, takes parameter t element. So again we'll say if not element is an instance of comparable, throw new non-comparable element exception. We'll pass in linked binary search tree as a string again. So here we'll say comparable of generic type T. We're going to do a cast, so we don't have to cast them every time. So comparable of type T, comparable element points to casted comparable of type T to element. So all it's saying is comparable element of comparable of generic type T points to our element which is being casted to comparable. So it basically just says comparable element points to element. That's it. That's all you have to know. So here we'll check if it is empty. So if is empty, root points to new binary tree node of type T, pass an element as a parameter. So here's where we're going to start adding our elements and removing them, finding them, whatever. So before we just had our general methods. So before we just had like how to traverse the tree with get left, get right, get the root, check if it's empty, get the size, get the elements of the nodes, set up the root to null and the traversals, that's it. We haven't done any elements being added or removed, so now we'll do that. So add element, root points to new binary tree node of type T, pass an element as a parameter. That's if our linked binary search tree is empty. So you can think of root like head or tail, well, head basically. So we're going to say root points to a new node, binary tree node of generic type T, and pass an element as a parameter. So it's going to store an object, which is our element, which can be any string or float, double, whatever you want to store, or any user-defined object type. So here we'll say else. So if it's not empty, so if our tree is not empty, that means we already have nodes in our tree. We're going to say comparable element dot compare to root dot get element. So it's going to say, okay, take the, because comparable element points to the element passed as parameter. See how that highlighted here? So we'll say comparable element dot compare to our root So it's going to check what's the root holding. If it's holding a string, it's going to use the Latin Unicode index. It has a value for every letter. But if it's numbers, it's just going to compare them less than or greater than. Same thing. So if, let's say our root's a 5 and we're trying to add a 2, or what do we usually use? We use 5, 6, 11, so we'll say our root's a 5. So comparable element dot compare to. So let's say our comparable element is 6 and we already have a root, which is 5. So we're saying comparable element, which points to the parameter we're trying to add, dot compare to our root dot get element. So what it's really saying is 6 dot compare to 5. And here we'll say is less than 0. So else comparable element dot compare to root dot get element is less than 0. So is it less than the root? Because remember, compare to returns negative 1, 1, or 0. So we're going to say if the comparable element, which is 6, dot compare to root, which is root dot get element, which is 5. So is 6 dot compare to 5 less than 0? No, that's false, because it should return a 1. But here it's checking if it's negative 1. So I add an else here. So there should be an if here. So if comparable element dot compare to root dot get element is less than 0, then we'll check here if root dot get left is equal to null. Then this dot get root node dot set left, so we're using a method chain, to new binary tree node of generic type T, pass an element. So it might get a little tricky at this point, so I'll try to explain. And then else, we're going to add the element, which is just going to call the support method we haven't done yet, so we're going to do that in a sec. So add element. We'll pass an element as a parameter and root.getLeft as the node. So all it's saying, okay, so if our binary search tree is not empty, then this block of statements will get skipped to this else. Then I'll say if the comparable element, which is, let's say we're trying to add 6, so if 6.compare to root, which is 5, dot get element is less than 0, so if 6.compare to 5 is less than 0, well, is 6.compare to 5 less than 0? It's not, because it's greater than 0, because it should return a 1, not a negative 1. So this statement won't get hit, it'll go to the next one. So at this point we'll put an else here. Then we'll say if, again, so else, then if root dot get right. So if it's not less than 0, then it's either greater than or equal. Because, right, you can do every node on the right child can either be greater than or equal to the node of the root. So we'll say if root dot get right is equal to null, then this dot get root node. So remember that method I said you could just call it get root? That's what it is. So get right, it's all from binary tree node. So I think it was right, we never used those linked binary tree methods with the special object references, object reference variables. I think these are unused. They're still unused. So we're saying here, if root dot get right is equal to null, then this dot get root node dot take the root node, and then method chain, this dot get root node, and then dot set right to new binary tree node of type T, pass in element, and here we'll call else, and then add element, and then root dot get right. So this part we're going to write that method in a sec, and here we're just going to increment mod count by 1. So mod count equals to mod count plus 1. That should be done. We just need the support method here. So the support method only works if the branch is not null. So if the child is not null, then it's going to continue to look for the place to add. Where's our main class? That's our method. Okay, so under the method here, we'll put adds the specified object to the binary search tree in the appropriate position. According to its natural, whoops, maybe I should double line that. Position according to its natural order. So what's its natural order? Well, a binary search tree has a natural order. If you have 5 as a root, then elements smaller than 5 will be on the left child, always, and elements bigger than 5 will be on the right child. So if you have a string, I'm not exactly sure the actual numbers, but you can check Wikipedia for the alphabet, the Unicode and Latin index. So if you have like lowercase t as a root, then for example like elements on the left child will be like ABC, and the elements on the right could be like XYZ. Something like that. It may not be exactly like that, but something like that. So one's going to be less than, and one's going to be less than, and one's going to be greater than always. So that's what its natural order means. So here we'll say note that equal elements are added to the right. As we said above here, if it's not less than 0, then it's either greater than or equal to. So here we'll say private void add element, takes a T element as parameter and a binary tree node of type T called node. And here we'll do the cast again, comparable of generic type T to comparable element, points to a casted comparable of type T to element. I'm just gonna have some water again. I might have to come back and do the rest of the methods because it probably will take another hour to finish it. I don't know if I'll be able to demonstrate all the methods in this video, but we will be doing another video with a decision tree and a decision tree I made. And actually there isn't, later on we'll do another video with the traversals just to practice. So don't worry about it right now. So we have private void add element. We did our cast here, so we don't have to cast them every time. Then we'll check again. Actually, we're not going to check if it's a instance of comparable. Here we'll just say if comparable element if comparable element dot compare to node dot get element, node dot get element is less than 0. So if comparable element dot compare to node dot get element, so take the node and retrieve its element. If comparable element, so if the parameter that we're trying to add, dot compare to one of the subtree's roots, basically, dot get element. So if it's less than the subtree's root, then here we'll say if node dot get left is equal to null, then node dot set left to a new binary tree node and pass an element as the parameter. So here it's saying, okay, well, if the node dot get left, so if the subtree's node dot get its left child points to null, which means that it's empty or doesn't point to an object, then we're trying to add an element here, right? So we're going to say, okay, we're going to add that element there because there's an empty spot. So we're going to say nodes dot set left. They're going to instantiate. What do we do when we instantiated a list? Linear node. We had to instantiate a whole linear node of generic type T points to new linear node of generic type T with element. We're doing the same thing here, just with a binary tree node instead of a linear node. So we're instantiating a complete instantiation of the node. We're saying node.setLeft and take our binary tree node here, set left to a new binary tree node and pass an element. So the first half of that object reference variable is basically here, and we're setting it to this one. Because here usually we have binary tree node of generic type T node points to new binary tree node of generic type T element. Here we just have node.setLeft. So what is set left? That's from our binary tree node class, so we'll go to that class. Go to set left. So here we have public void set left takes parameter binary tree node of generic type T node. So it's saying, okay, take the left binary tree node object reference variable and point it to the node, because every binary tree node has a left and a right child. Oh, where were we? So here. So we're saying, okay, since it's binary tree node, this node here, right, set its left to a new binary tree node element, because add element here, this add element just takes, this original method just takes one parameter T element. So once we're saying it's not null, so if the root.get left is not null, so if it's trying to go down from the root to its left child to its left child, it's trying to find a empty edge. So it's going through the subtrees. They're saying, okay, the elements are full. Where can we put our next node? So if it's not null, they call an add element method with two parameters. So okay, so where's that? It's down here. So it's going to say, okay, well, we were carrying the element down, and we have our node here, binary tree node. So it's going to say, okay, if the root dot get right is equal to null, then set its right to the element. But if the root dot get right is not null, then call add element and pass in root dot get right, which points to a node. Then it's going to say, okay, well, let's pretend it says left, root dot get left, this one. So it's going to say, okay, if the node dot get left is equal to null, which was the original root of that subtree, then it's going to say, okay, well there's an empty spot, we're going to add our node here. So I hope you understand that part. We'll do a walkthrough again. So if it hasn't found a spot yet in all the nulls, all the binary tree nodes are holding an element, then we'll say, okay, call element, do a recursive call, I guess. Pass an element as a parameter and node.getLeft. So it's going to keep searching for an empty space, a memory location that isn't storing an object, or in this case our tree. An empty, it's looking for a leaf basically, it's looking for an empty leaf, not a branch with a subtree. So if our element is not less than 0, so if it's greater than, it's going to go on the right side, greater than or equal to. So don't worry, again, we will do a walkthrough in the debugger. I probably will take a break pretty soon, and I'll come back, we'll finish the rest of the methods, and then we'll do a walkthrough of these adding and removing elements. So here we'll write else if node.getRight. If node.getRight is equal to null, then node.setRight to new binary tree node of generic type T, pass an element as a parameter. Then say, so if it's so here we said if the node.getRight is equal to null, so there's an empty node for us to place our added element. So if it's not null, then do the same thing, call our add element recursive call again itself, right? And then node, and this time change the node to add it to the getRight child. That's it. That's all it's doing. And we're missing a bracket somewhere. Okay, it's over there. So add element node.getRight. It's a void, so we don't need to return anything. And that's it. So we'll take a break and we'll come back.